Здравствуйте, добрый день. Good morning, good afternoon, wherever you may be. A warm welcome to you all to this British-Kazakh Society webinar, Earthquake Hazards, Risks and Pathways to Resilience in Kazakhstan. I'm David Hardy, a director of the British-Kazakh Society and chairman of its education group. The session will be in English and Russian, and you can choose your language with the button at the bottom of the screen. Please type in your questions using the Q&A section, and they will be answered at the end of the session. I'm delighted that our moderator today is Iqbal Hussain. Iqbal is a geoscientist at the British Geological Survey, Multi-Hazards and Risk Challenge Area. He's a particular interest in using satellite Earth observation techniques to help address problems in international development, particularly in the areas of disaster risk reduction, climate change, poverty, and global health. Kazakhstan has a long record of large earthquakes. The potential for earthquakes presents challenges in assessing hazards, modeling risks, and building resilience for urban growth and the development of energy and transport infrastructure. Today, the panel will show how the historic and prehistoric past can be used to help inform where earthquake hazards are present, and we'll discuss some of the ways in which increased knowledge of hazards can help reduce risks. They will emphasize how the effects of earthquakes are not confined within national borders, presenting opportunities for international cooperation and knowledge exchange. Our distinguished panelists are Richard Walker, a professor in the Department of Earth Sciences, University of Oxford. Richard has spent over 20 years researching earthquake processes and their societal effects, with a current emphasis on the Central Asia region. And Aydin Mukambayev, who is a seismologist, the deputy head of Kazakhstan's National Data Center in Almaty, and a researcher at Kazakhstan's National Nuclear Center. He has a wide-ranging interest in seismic monitoring and earthquake hazard assessment. Iqbal, over to you.
Thank you. Thank you, David. I will share my screen. I'm just wondering, do I have the ability to share again? It's not allowing me to share the screen.
Yes, Iqbal, you should.
It's just changed from earlier. Can I ask you to share the screen, Alizan? Because it's not allowing me to share my...
Yeah, all right, just a second. Please go ahead without slides for now.
Okay, thank you. So, good day, everyone. It's great to be here and to moderate this panel discussion. I want to spend 2 minutes to give you the broader global context of what this panel discussion will go into more detail. Globally, 2/3 of all deaths arising from earthquakes, arising from natural hazards in the last few decades were caused by geological hazards. And most of these fatalities were due to earthquakes. Earthquakes, in addition to fatalities, have caused around $1 trillion of losses in the last 20 years. Most of this loss has been from a few very high impact events.
Sorry, Iqbal, can you see the slides?
Yes. Oh, next, please. And so a few very high profile events have caused most of this loss. Some examples include the 2023 Turkey earthquakes that have caused over $100 billion of losses, economic losses, and the 2008 Sichuan earthquake that caused over $150 billion of losses. Next slide, please. So thankfully, these big loss-producing events have not occurred in Kazakhstan or in any of the Central Asian regions yet. However, Kazakhstan's economy is rapidly growing. Its infrastructure expansion is happening at a very fast pace. So what we want to do is understand, could such a major loss-producing event happen in Kazakhstan? And if that were to be the case, how can we prevent such a scenario? And in this panel discussion, these are the questions we want to address with our colleagues, Richard Walker and Aidan from the UK and Kazakhstan. So if you can close my slides, and then I'll pass on to Richard to give an overview of the historical context of earthquakes in Kazakhstan, and Aidan to give you more understanding of the current approach to monitoring and understanding resilience. Over to you, Richard.
Wonderful. Thank you ever so much, Iqbal, for that introduction. Thank you to the Society for the invitation to talk to you today. I'm just going to start this and go back to my first slide. So I will talk through some of the context of earthquakes and also related hazards. Earthquakes can cause landslides, can cause flooding. There's lots of interactions between these things. And I'm going to give some examples from Kazakhstan and also the impacts in wider parts of Central Asia and Asia. These are often international problems that require international efforts in order to increase our resilience. The work that I will talk through has been very long-running collaborations between our own team in Oxford University in the UK and with institutes in Kazakhstan, including Aydin's institute, the National Nuclear Center. We have had various different programs. At the moment, we are funded through the UK government, through the FCDO, the Foreign, Commonwealth and Development Office, through the Central Asia Water and Energy Programme, with an emphasis on hydropower and other energy infrastructure. If we start from a very large scale, this is a map covering large part of the globe, going all the way from Europe through to Eastern Asia. And we can see three areas: Africa, Arabia, and India. All of these are moving northwards, tectonic plates moving northwards relative to something we may describe as Eurasia. Red dots within this map represent significant earthquakes that have occurred in past decades. And you can see from the distribution of those red dots that the earthquakes occur widely. Earthquakes within continental regions, so including within Central Asia, are widespread. But in any one place, there may be a gap of many thousands of years between them. The overall plate motion, so the movement of India relative to Eurasia, is about 5 centimeters per year. And if that is divided over many faults, many areas over a zone 2,000 to 3,000 kilometers wide to the north of India, then each area will experience earthquakes very rarely. Okay, it will take thousands or sometimes thousands of years to store up enough motion for that to be released in a large earthquake. And so therefore that presents us with a challenge. We need to be able to understand or find ways of understanding the earthquake record over appropriately long time periods. And this means, and what is the solution to this? How do we overcome this challenge? It means that there is a place for many different methods to be applied. We can make detailed measurements of what is happening now, and we can use things like seismology, instruments that record earthquake waves, and these are things that Aydin will be talking about in his talk later on. Satellite measurements are increasingly important to show areas where earthquakes are occurring, or to show where they may occur in future. But also, we need to bring that together with longer time periods. If we want to know what kind of earthquakes might occur and what effects they may have in future if they reoccur, then we need to go back into historic time periods, prehistoric time periods, and even geological time periods, using techniques that we call paleoseismology, the study of ancient earthquakes, or a more wider term, earthquake geology, the application of geological methods to the study of earthquakes. One thing that I want to stress is that at present, we have only imperfect data. We haven't done everything that we might need to do to make our societies as resilient as can be. We have only imperfect data and also uneven data. Some places more exists, some places less. And so I want to get across the fact that there's still a lot of work to do. Of course, earthquakes are a problem societally. They are also a problem economically. On the top here, this is a plot that reiterates one of the main things that Ekbal described, in that earthquakes are very damaging in terms of human life. And when we look at this plot, the size of the circles here, these are earthquakes that have killed people over a threshold of people in individual earthquakes, and the size of the circle represents the level of the death toll. The color of the circle represents the magnitude of the earthquake. And there's a couple of take-home messages from here. The interior of Asia has hosted many earthquake disasters in terms of human life, and it has a long history of these. The other thing to get across is it's not always the largest earthquakes that have caused those disasters. Even moderate-sized earthquakes, if they occur in a place with vulnerability, and that can be, from the types of building or the types of infrastructure that exists, the population densities, we can still generate large death tolls. On the lower panel, we talk a little bit more about infrastructure. And this is, again, something that I see and I want to frame as an opportunity, because we are going through an age of rapid infrastructure building, whether this is transport networks, both nationally and internationally, which I show on this, I show an example on this figure, but it can also be energy infrastructure, hydropower plants, nuclear power plants, and traditional pipelines, etc., and oil and gas infrastructure. If we're talking about the Caspian Sea, many things are being developed, many things are being built. Also resources, again, all of these things require infrastructure, and that infrastructure, we have an opportunity now, because this is new, to really ensure that things are as resilient as possible if we build our underpinning knowledge. We keep on talking about the word earthquake hazard. What do we actually mean by hazard? Well, typically what we're talking about is the probability, so the percentage chance that a certain place will experience ground shaking of a certain level over a certain time period. Right? So if you're talking about buildings, dwellings for humans, we may be talking about 50-year time periods. We're interested in the percentage chance that building will experience strong shaking over that time period. If we're talking about critical infrastructure, a nuclear power station, then obviously we'll be interested in much longer time periods. How do we build that understanding? A lot of this comes from seismology. So using the distribution of small earthquakes that are recorded by seismometers, and applying metrics to these to understand how, or to estimate how often on average larger earthquakes may occur, right? So you can start to build up some impression of over what time periods you may expect to see strong shaking occurring in any places. So we require seismological data. Increasingly, we're adding in other types of data as well, satellite imaging data, etc. And you end up with a map such as this. This is a global compilation from the global earthquake model, GEM, from 2023, and the colors represent the different kind of peak ground acceleration that might be expected over a period of 475 years. This is called a probabilistic approach. It's all about probabilities of things happening. And this is very useful. It's very helpful in setting design, let's say the design specifications for buildings, so the construction policy, for planning about what kind of things might be occurring over different time periods. But it doesn't tell us where and what effects will be affected by by individual earthquake sources. Another type of earthquake hazard that is often talked about is then this more what is called a deterministic approach or a scenario approach. Here, this is in this map, we have Isyk, this outline here. And what we've drawn on here is the 1911 earthquake rupture. So this was the one that affected Almaty in 1911, the Chonkemin, Chonaksu, now in Kyrgyzstan, just in the mountains north of Isyk. But we can generate or make a synthetic earthquake from that rupture. And then we can estimate what the shaking would be in the area around. And so we can estimate the effects of a rerun of that historical earthquake. And so you could see the levels of shaking that would be expected. And these can give a much more granular view of what would happen from particular earthquake sources. Okay, so and these are then very useful if you want to understand the overall effects on a city or a particular, or a dam or a nuclear power station. Finally, we also talk about fault displacement hazard, the actual kind of breaking of the ground in an earthquake. And this is an example from New Zealand. There's an earthquake rupture running through the ground here. See this road here used to join up with the road over there. And this house was built right over the fault. This fault was not recognized, so people built over it. The construction levels were of such a high standard here that the house actually stayed upright, but it was dragged off its foundations. You can see its foundations some meters away from the house, even though the house did not collapse. Nonetheless, the ideal situation is that if we know where faults are, we avoid them. And we build setback safe areas around the faults that we have no construction. If things actually cross the faults, we make sure that they're mitigated for pipelines, etc. Right? Sometimes you can't avoid faults, but you can make sure that the engineering is in place to cope with potential fault displacements. But also earthquakes cause other things. So we often talk of secondary hazards. So, things that are caused directly by the earthquake. A landslide, for instance, landslides are often caused by earthquakes. But also, increasingly, we talk about multi-hazards because a lot of the hazards that we see, earthquakes, landslides, flooding, rainfall, climatic change, all of these things have interplays and sometimes in quite complex ways. And so increasingly, we try and build things into what is called a multi-hazard framework so that we can actually see how all of these things might affect each other. This is an example from Tajikistan. This is the Hait earthquake, 1949. The majority of deaths in that earthquake were caused by a large landslide. Here is the scar of that landslide. Here is the debris. You can still see it. Here is the town of Hait. And it actually covered a large part of the town, causing many fatalities. Or within Kazakhstan, this here is Kolsai National Park, and I think Aydin may talk a little bit more about this. But the road to the national park is this one. A few years ago, this landslide was set off. Large amounts of rainfall had saturated the ground. A small earthquake actually set this thing going, and over a period of 4 days, it almost cut the road to the national park. It almost blocked the river. if it had, it would have caused a ponding and potential flooding of the river. So you can see how these multi-hazard chains can easily start. So again, with preparation, we can actually start to see how these things, where the vulnerabilities may be.
Richard, just 2-minute warning.
Oh, wow. Okay. So I've already spent a lot of time. Just to say that ground shaking, we need to turn that into risk. So we need to know the vulnerability. Typically, you look at how strong the buildings are and how they would respond if you have earthquake shaking. And so if you have information on different types of buildings, these are actually for Almaty, and also the concentration of buildings, you can turn that into maps of risk. So here's distribution of different building types and density of building types across Almaty. Let's apply that to Almaty city. We know that Almaty was very badly damaged by 3 earthquakes: 1887 Verni, 1889 Chilik, and then 1911 Chon Kermin earthquakes. There have also been earthquakes that have shaken Almaty in recent years. One relatively small earthquake close to the 1911 rupture. Also, in January of 2024, there was a large earthquake, but actually at quite great distance from Almaty, right? So, again, this trade-off, you have similar effects from a small earthquake nearby and also large earthquakes at further distances. We can look at the landscape for evidence of faulting. Here is a fault, and if you have movement and it lifts up this side, it creates topography. That topography can offset features such as fences. It can also have an effect in terms of the rivers, signatures in the landscape that we can observe. And here is the 1911 fault scarp. So you see it moving along here, right? This was actually mapped after the earthquake, and there was a very famous book published in 1914 by Bogdanovich and others, where they actually mapped. This is one of the first really scientific post-earthquake surveys of faulting. That earthquake rupture is still visible in the landscape. Here we are in the Chonaksu Valley, and you can see the fault scarp. We can use similar methods to identify the 1889 fault scarp, the Chilik earthquake. Here it is running through the landscape near Sati, near the Kolsai National Park in Kazakhstan. This was not mapped at the time, but we can use our observations to identify it. We can go back in time. Here is Almaty city, and if we actually use those same kinds of approaches, right, looking for these steep places where faults might be, we can actually identify them, sometimes even in the city itself. The road is level, it steepens, and then it continues. And this is actually a fault scarp, right? This is not one that has caused a historical earthquake, but it is there, and it will have been generated in prehistoric earthquakes. We can also identify other faults. So here we're using an elevation product, and if you draw these profiles through the landscape, you can see the ground kind of lifting up and then dropping back down again. This is very diagnostic of faulting, and this is a fault that's out in the northern districts of Almaty. And so we could take all of those fault sources, and we can generate synthetic earthquakes on them, and we can look to see what levels of shaking they would have. And from the demographic information, building density, types of buildings, population, we can then estimate what those would do in terms of their effect on the city. I show here economic cost, millions of dollars. We could also show fatalities. We could show estimated damage to buildings. But you can see that some of these are the 3 historical earthquakes, 1887, 1889, 1911. But some of the others actually have distinctly different risk profiles. And so learning more about the geology actually helps us to potentially understand what the risk profile, the overall risk profile to Almaty might be. And that's important for a whole range of reasons, from purely economic reasons, but also through to informing risk reduction activities. And, when we get to this point, we kind of, we can start to think about how can you start to reduce that risk. We can never reduce it to 0, but nonetheless, there are sometimes some steps that can be taken to try and approach this: education, capacity strengthening, learning more about the hazards themselves, right? We've shown quite a limited number of works that we've done, but there's lots more that could be done.
Richard, I think we're running out of time.
Wonderful. Okay, so I'll just very quickly say, in terms of, but a lot of the focus is on infrastructure, and a lot of the work we're doing with colleagues is on, hydropower, right? Again, international problems, large projects, putting in the information now before things are built so that we can ensure that things are as resilient as can be, right? So i.e. it's much better to do it now than to find out about things later. We're doing this kind of work in the Tian Shan, but we also have projects in the Caspian Sea region, and particularly things such as submarine landslides. And again, trying to understand the risk profile, the Caspian Sea being important for a whole bunch of reasons, from energy through to the transport, and to try and build those underpinning data sets relating to hazards. I'll leave it at that. Thank you very much.
Thanks very much, Richard. Really interesting overview of earthquake hazards themselves, but also why they're so relevant to Kazakhstan and the broader region. Thank you. Just in interest of time, just quickly moving over to Aydin, if you would like to start your briefing. Thank you. You are muted, Aydin. If you could unmute yourself first.
Thank you very much, Iqbal, and thank you for the opportunity to give a talk about seismology, hazard risk, and clear seismology in our country. My presentation I want to give in Russian language. Can I start?
Please go ahead, please.
Добрый день, коллеги. Моя презентация касательно...
Good morning, colleagues. My presentation is about seismic monitoring, and also it's about hazards and risks. And I'm also going to talk about cryoseismology. It's a science that studies glaciers using various seismological methods. My presentation consists basically of 4 parts. The first part focuses on seismoacoustic network of the Institute of Geophysical Research of the National Nuclear Center. I'm also going to talk about the treaty on nuclear tests. I'm also going to talk about the earthquake catalog and how we use it to assess risks, etc. Also, I'm going to talk about the active tectonic study and international cooperation in this area. And then I'm going to talk about cryoseismological investigation. Next slide, please. This slide shows you the locations of the stations of our nuclear center. Some of them have 3 components. In blue, you will see the so-called seismic groups. One group consists of several seismic stations, ranging from 10 to 20. In red stars indicate the locations of some kind of stations. The National Center has 7 3-component stations, 5 seismic groups, and 3 ultrasound groups. These stations were set up as part of the Treaty on Prohibition of Nuclear Tests, and these stations are part of the international monitoring kind of framework. All data from these stations are received by the Kazakhstani data center, which is located in Almaty, and this data center performs the following functions. Basically, it receives data from these stations. That's number one. Number two, it processes these data. Then it is responsible for exchanging these data with all sorts of international and national centers, data centers, and also it's responsible for conducting international research in the fields of geodynamics, seismology, etc. Here you will see a map of all seismic events for 2024 that were registered by this framework, by the system. In red, you will see earthquakes, and in yellow, you will see locations of those seismic events that are connected with explosions that are usually conducted for extraction purposes. As you know, Kazakhstan has a lot of mineral resources, and so many companies involved in mining, they conduct explosion works for extraction purposes. And our work, obviously, we work internationally, we cooperate with organizations globally. Since the data from these stations are open and accessible, the global seismological community can have access to these data. And also we do some joint research work. And here I have a list of large international organizations with whom we work and cooperate. Results of processing of data from these stations are published on our website. Everything, absolutely everything, is available and open. Anyone who wishes can have access to these data. Also, we publish some news by our center does that. Also, we publish our research studies and publications there, all research work that was and is being done with all our colleagues from all over the world. As I have said, some of our stations are part of the international seismal monitoring framework system. This slide shows you a map of the international monitoring system. The system comprises 4 elements. Number 1, seismic stations. Number 2, infrasound stations. Number 3, radionuclide stations, and hydroacoustic stations is element number 4. On the right-hand side, you will see a diagram which shows you, for example, the Makachi station. It's part of the primary stations list. Overall, there are 50 stations like that, and our Makachi station is in the top 3, in the top 3 stations. Also, we have a station which is part of the system that comprises 120 stations, and this station is one of the best actually in the world. And this means that the stations of from our system are quite informative and quite sensitive. On the right-hand side, you will see a map of earthquakes that was registered by this IMS, and Makachi was part of that sort of project, and Makachi basically sees the whole globe, is able to sorry guys, it's a bit technical. Next slide, please. Now, let's move on to the earthquake catalog and the hazard map. Next slide. As I have said, the data center is responsible for processing data from the system, and data processing is conducted in 2 stages, automatic and interactive. Starting from 2006, the data center has been taking part in all sorts of international projects, and the focus has been to evaluate seismic hazards, not only in Kazakhstan, but for the whole of the Central Asian region. We had a project which was implemented in 2025, and the data center was responsible for creating this earthquake catalog. The next project is the earthquake model of Central Asia. This is part of that global project which Professor Richard has mentioned earlier. And EMCA was focusing on Central Asia, basically. And Kashabu is a project where we did even more work. We focused on bulletin stations. We collected primary information from there, and then using modern software and high-speed models, we sort of were able to verify all seismic event data and information. And the last project in which we took part is the development of the information framework for the seismic zoning map Kazakhstan project, which was implemented in 2016. This is now part of the national construction standards, and also it comprised the seismic zoning, creation of the seismic zoning map of East Kazakhstan. And the main organization that were responsible for the earthquake catalog was our data center. And all catalogs were used then, after that, for evaluating hazards, assessing relative hazards, not just for Kazakhstan, but for the whole Central Asian region. And here you will see basically how various Central Asian organizations contributed into creating this catalog. In yellow, you will see the information from our center, and the gray is the contribution of the English seismic center, but all data that we process and all our bulletins and catalogs, we provide all that to the International Seismological Center. Next slide. Here, this slide shows you a map of the seismo-generating zones of Kazakhstan. To create this map, both historic and up-to-date modern data was used on faults and active tectonic faults. And so we used them and come up with the maximum magnitude of earthquakes that can take place along these faults. So we call them the seismo-generating zones. And based on that information, then you can come up with the level of hazards and risks arising as a result out of those, earthquakes. And government construction standards, by the way, when they were developing those, they used this map and then two more maps. The MSK map 6.4 and the peak acceleration of ground map. As Professor Richard has said, this map was prepared for two periods with the 5 or 10% probability over several thousands of years. Next slide. By the way, this map shows you the intensity of earthquakes and the peak acceleration of ground for these two periods. Next slide, please. As all of you know, in Kazakhstan right now, a lot of work is being done to select a site for a nuclear power station. And the head of state announced that in Kazakhstan, actually, there will be several nuclear power stations built. And right now, with Rosatom, which is a Russian company, Three sites are being sort of evaluated. As you know, there are various international standards that we need to comply with, geological and other standards. And so when selecting a site for a nuclear power plant, you do need to evaluate and assess seismic risks and hazards. You need to study geology and faults and everything else on this site. And so if there is an active fault within this site, then this site should be excluded because obviously faults may lead to a lot of destruction. And that's the reason why such work is extremely important in that we should be very careful when selecting a site for a nuclear power plant. Next slide. These works are conducted in a comprehensive manner, as we say. Not only seismology and geology are being taken into account, but also geotechnical and other data are being taken into account, and everything sort of is being analyzed so as to then see whether this site can be selected or not. So if there are certain landslide risks or flooding risks or tsunami risks, hazards, and all other risks. So everything put together is being sort of analyzed and assessed and evaluated. This is done not just at the initial stage of the site selection initial stage, but this is done also during construction, during commissioning. This is an ongoing sort of process whereby all risks and hazards are constantly evaluated and assessed. And after when, for example, this nuclear power plant is commissioned, you need to also continue this observational and evaluation and assessment work.
Quickly, 2 minutes.
Thank you.
Yes, at each and every stage, reporting is also done. So to select a site, we gathered all information about the seismology of this area, about the number of faults in this area, and all of that is used to evaluate threats and hazards. And all this information is basically used by all involved before construction starts. And basically all this work is done to be able to predict the probability and also to assess and evaluate risks and hazards. Now, allow me to say a few words about our international cooperation. So this work was started together with our colleagues from the Oxford and Cambridge universities. This was the Earthquakes Without Borders project, headed by Professor James Jameson, starting from 2012. We took part in various field work together with Professor Richard Walker, and we studied active faults in Kazakhstan, more specifically in the Almaty and Zhitosu regions, oblasts. And so we basically also worked on the Zungarsky fault in the area of the Chilik earthquake, also in the suburban areas of Almaty. By the way, next slide. Let's go to the next slide and I'll show you some examples of what we did. The Drungaria project, we looked at the various faults there. We did some trenching work using various seismological methods, and so all these works were done together by us jointly, and we came up with the digital landscape of the surface. We used various balloons back then, but now we use Sputnik imaging of high resolution. We use drones to see what movements took place, and then all that information is usually used to calculate all sorts of things such as segmentation, fault segmentation, and then forecasting of the magnitude of a possible probable earthquake. And so we basically came up with these rupture scenarios to be able to sort of forecast what the magnitude of earthquake number 1 could be and earthquake number 2 could be. Next slide. This information is used for modern seismology purposes. We use the catalogs here and such parameters as earthquake mechanisms, and together with all that, putting everything together, we come up with the fault. Guys, I'm sorry, I'm a bit challenging. And so all these works were done by us jointly with our international colleagues and partners, and thanks to financing from our English colleagues and thanks to Professor Richard Walker, we held a field workshop for researchers from South Caucasus and Central Asia. By the way, this scientific field, is not a well-developed field, scientifically speaking, in our countries, unfortunately. And so for us to be able to expand sort of our knowledge and to share knowledge with each other, we decided to hold such a workshop. And the main objective of this workshop obviously was to train specialists from all sorts of organizations in how to use modern methods. And also we wanted to create a platform on which we could exchange our knowledge and experiences. And so hopefully we'll be able to also come up with joint projects going forward. As you know, earthquakes don't have borders, and when we work together, we obviously will be able to do more. And so all that was held in the Chilik earthquake area. As you know, the Chilik earthquake was quite a strong one. The magnitude was 7.3. And so during that workshop, we trained our colleagues how to work with GPS equipment, with imaging, Sputnik imaging, satellite imaging, how we also taught them how to do trenching work, how to use all sorts of equipment. And also we had a series of lectures during which trainees were able to gain a lot of information, and also it was practice-oriented.
Aidan, can I ask you quick if we could wrap up and then we can have some time for discussion?
I almost finished, just a few slides. И это все происходило на том месте, где...
So all that actually took place in the active fault area and in the area where we have a lot of landslides. So we were able to demonstrate all these things. Kulsaik, these lakes, as you know, that are located in that area, actually appeared as a result of the earthquake. And also, we wanted to provide support and assistance to younger colleagues for them to be able maybe to take part in conferences going forward and to cooperate with that. And so we also had some materials published. All in all, 38 trainees from different countries took part in this workshop. Next slide, please. Next slide, let's keep this one. And now I would like to say a few words about, again, the money that we got from our English colleagues, and 10 people took part in the conference in Tashkent in April, together with Uzbekistani and Kazakhstani colleagues. We did some imaging of the earthquake, which took part in 2018. Next slide, please. And a few words about cryoseismological investigations. Next slide, please. Over the past 3 years, we have been working on the following project. We basically looked into glaciers using various seismic methods. The first publication was in 2018. Also, we won a grant, and that will enable us to do some more detailed work. And we are studying the Tianshan sort of area in China, and there we have 3 seismological stations. Next slide, please. And we used data from 6 stations to be able to process, to analyze these events. We're basically now accumulating, sort of gathering data. We also submitted another application. Zone number 2, for example. Zone number 1, we have ice, glacier earthquakes, and in the second zone, we have tectonic earthquakes. And so they're different in terms of when they happen, and yeah. Next slide, please. These studies rather are important, not only for climate change purposes, but also for us to be able to maybe predict all sorts of phenomena such as melting of glaciers.
Alexander, maybe it's time we can end here and just allow a few minutes for discussion, if that's okay. I think we've covered quite a lot of material, and we have only a few minutes for questions. So in that time, can I ask our participants if they have any questions, if you could type it into the Q&A, and I can help get some of these answered. We already have 2 questions, and maybe we'll just start with those rather than, if that's okay with Richard and Aidan. The first question is around the specific locations of the nuclear power sites that you mentioned, Aidan. Maybe you can comment briefly on that.
Площадка выбрана на берегу озера Балхаш.
One site was selected in the following location, the Balkhash Lake area. And right now we are gathering materials, looking into geology, geotechnics. There are some stations that accumulate and gather data for that area. Also, on top of that, we are working with literature, relevant literature, and hopefully we'll be able to come up with a comprehensive evaluation of seismic risks and hazards.
Okay, that's great. Richard, anything to add on that?
On the nuclear power, I think I didn't mention about where they are. We could move.
Yes. So that question summarizing is around are we estimating the seismic hazard in Kazakhstan, and where in Kazakhstan, which faults are capable of generating particularly damaging earthquakes?
Okay, I mean, I could say something. Egbal, you may well have something to say as well on this one. But I mean, yeah, I think, I mean, there's one challenge we have in Kazakhstan in that a lot of these earthquakes, when they occur, are large on faults that are moving slowly on average, and so the recurrence intervals can be very long. And in some of the examples we've seen, large earthquakes occurred. 1889 occurred on a fault that maybe made the last earthquake 10,000 years ago or more, and actually, broke a number of small faults to make one big earthquake, and so a lot of the behaviors are quite challenging within the kind of frameworks that we use in earthquake hazard. That would be somehow my feeling. Most of the big faults are in the mountains, right? There's a correlation between that, but also as we go out into the steppe and we go to the places where nuclear power sites, etc., have been proposed. It's important also to look, because we don't know that there is a lack of recent earthquakes in that context actually means that there's a lack of earthquake hazard. What do you have anything to add on that, Egbal?
I would actually pass it to Aydin if you have any other further comments on your particular areas of concern in Kazakhstan for potentially damaging earthquake.
Ну, как я говорил до этого, что есть карта сейсмогенерирующих зон, и каждая
As
зона
I have
имеет
said, we have the seismic generating map, and each zone has its own level of magnitude. Northern Tian Jungaria, we have faults there in those areas that are seismically dangerous, 7.58 up to 8. The Chonkimin zone of faults, the Zalisky zone of faults, the main Jungarsky fault, and other faults. Those can generate pretty strong earthquakes with a magnitude of 7 and higher.
So the only other thing I would add to that
Yeah, we should. Sorry,
that,
guys.
oh, sorry, I didn't do, yeah. The only thing I would add to that is that it's not always about the bigger earthquake that we need to be concerned about. If we care about impact, it's all the location of these earthquakes. So even a small earthquake in the wrong place can have a very high level of impact. So while we may understand these very large fault networks that exist already in the mountains, as Richard and Aydin have said, and we know where some of these are, and they can produce very large earthquakes, my other concern would be about where we don't have big mountains, but we yet could have a small earthquake. But a small earthquake in the middle of a city can have a very dramatic levels of impact. So that's where I would also add an extra concern that
Can I just ask a quick question, gentlemen?
Sure, please.
And as you know, the British-Kazakh Society has instigated a number of expeditions. We're running a pilot expedition this year. It's 2 stages, and stage 1, we're taking young scientists onto the glaciers of the Tian Shan to monitor the glacial melting. And what's the potential impact of earthquakes on the glaciers and the consequences for water supply in Almaty?
I think this is a great question to you, Aydin. If you could start, maybe Rashid can comment.
Спасибо, Дэвид, очень хороший вопрос.
Thank you, David. That's a great question. Yes. Some parts of Almaty do use water, as we say, from glaciers, from the glacier lake that we have up there in the mountains. And so if an earthquake happens, then there's huge risk. I mean, of huge flooding, basically. And so those lakes that we use for water supply purposes and other purposes, so as a result of this avalanche, obviously, yeah, that will be bad. So as a result of avalanches, obviously people will be impacted and buildings will be impacted. And number 2, we will lose one of our water supply sources also.
Yeah, and I guess I would just say, as again, to reiterate that everything is linked when we're looking at hazards. if we're looking at the water aspects, whether it's glacier, could an earthquake cause destabilization of a glacier, or could it produce landslides that affect the flow of water that we rely on? Lots of these things are connected, and we're going through a time period where we're having to adapt. We're having to kind of, grasp the fact that the world is changing, and we're putting in new structures, whether physical or policy based, to deal with these. And this is then an opportunity to actually make sure we incorporate as wide an array of resilience measures as possible, right? So making those connections now, building underpinning data sets that we rely on, that we can then we can use afterwards. It's much better to do things now than having to deal with the effects later. I think that would be my end message.
And I think that's a great message to end on. Thank you, Richard. And over to you, David.
Well, thank you very much. I found that absolutely fascinating. I've learned a great deal. And who knows, our forthcoming expeditions, we might want to come back to you and involve you in some of the work there. That would be very, very interesting. So a very big thank you to Iqbal, to our panelists, Richard and Aydin, and to Alijan, working hard behind the scenes, and our interpreter. The British-Kazakh Society has some events coming up in the next few weeks. On the 18th of June, we have an interactive discussion on arbitration. The 23rd of June, the UK and Kazakhstan trade and investments. We have an in-person event hosted by Field Fisher in London. And then on the 8th of July, a seminar on UK and Kazakhstan tax legislation, really quite different from earthquakes. We always welcome new members to the British-Kazakh Society, and details are on our website. So finally, thank you very much indeed for participating, and we look forward to seeing you again soon.